Hi, good morning. My name is Manoj. I'm a currently PhD student from the University of Leeds. Thank you so much for this opportunity. Uh, yeah, I think you guys might have already heard a lot about osteoarthritis, cartilage, biological studies on that. How are we going to use biomarkers in order to identify how the osteoarthritis progression takes place and everything. Basically, I'm a mechanical engineer. In that, I'm a tribologist. So I just want to give a brief introduction. Also, sorry, these are the disclosures of my supervisors and myself. Yeah. Before starting this, I want to give a brief introduction about the tribology, what I'm doing here. So tribology is the study of friction, wear, and lubrication of any material interface. So what I'm doing in this project is we are looking into the biotribological properties of the cartilage. That means we are studying friction, wear, and lubrication of the cartilage. So why are we doing this? Because as an engineer, I see any material as a material with a different mechanical properties, different tribological properties, how does it fail, and things like that. So my main interest in osteoarthritis is, as a material, cartilage fails in the osteoarthritis due to a lot of friction, due to failure of the lubrication. So as a tribologist, I want to understand what is the mechanism or what is the progression that takes place there. So as we all know that osteoarthritis is one of the biggest problems. So how are we going to contribute engineering way that we can help in developing a kind of lubricant-based solutions and other treatments? So what we are doing is we are trying to understand various mechanical and tribological properties in the healthy and the osteoarthritic cartilage. So as we all know that there are lots of studies where they have identified different properties in the cartilage, where they see the reduction in the aggregate modulus, permeability, tensile and shear strength in the case of the degraded cartilage. And tribologically, they see that the surface is damaged, which means if a surface is damaged, let's say if the surface is rough, then the friction is high. That's the main thing what we are looking in a cartilage as well. And what is the main reason for that? There's no lubrication. So the synovial fluid does not provide a proper lubrication in the case of the osteoarthritic cartilage. So why and how does it fail? So that's the whole study about. So what am I doing as a methodology in my experiments? So we are taking the degraded cartilage in the osteoarthritic knee joints from the patients undergoing joint replacement surgeries, and we are trying to do the Raman spectroscopy on the surface in order to identify what are the different kinds of damages what has been occurred in that particular degraded region. So then we are characterizing those regions using two different techniques of qualitative and quantitative analysis, which is the histology and SCM characterization. From that, on the same regions which we have identified, we'll be doing a microindentation in order to study the mechanical performance, and we are doing the tribological experiments in order to understand the friction coefficient. And finally, this will help in validating the emerging medical technologies, which means when a person develops a lubricant-based solutions, we can use that solution in a testing setup and see if that solution is providing whether the lubrication or not. So that's the loop there. And coming to the grouping of cartilage. So what we are doing is, as I told earlier, we are taking the degraded cartilage, we are doing the Raman grouping in this. How are we doing the Raman grouping? In Raman spectroscopy, we are trying to identify where is the increased collagen damage, where is the increased proteoglycan damage, increased bone mineralization and crystallinity. How are we doing this? We are trying to see the Raman spectra for that particular proteoglycan, collagen, and carbonate crystallinity intensity ratios, and then we are seeing where there is a high damage, then the intensity ratios are high, and then based on that, we are grouping it in a 5 different way. In the group 1, we see the high collagen proteoglycan damage. In the group 2, we see high collagen and proteoglycan damage. 3, where there is high collagen, proteoglycan, and carbonated crystallinity in the same way. So based on this grouping, we are characterizing each group, seeing mechanically and tribologically. So how does this group looks like? So when, as an engineer, we can group anyway, anything, but it has to be clinically relevant, right? So when I'm saying that this is the property, how it is changing, if I explain it to a doctor, he has to understand like what is the use for him when I'm showing this. So in order to do that, we are trying to see how does this groups look as a healthy cartilage or as a degraded cartilage. In the group 0, where all the composition there is no damage, the cartilage looks intact without any damage. In the group 1, the cartilage has severe erosion on the superficial layer, and in the group 2, there is uneven distribution of the extracellular matrix with complete erosion and exposure to the bone. In the group 3, there is complete erosion as well as a crystallinity on the bone. And in the group 4, there is an erosion with more bone damages, and there is a little bit of debris on the ischium. I'll say why this group 4 is very important, because we need to see that there is a lot of debris with the bone damage. I'll come in the last slide why that is important there. And in the group 5, there is increased bone damage and there is no cartilage at all. It is exposed to the bone. So these are the variations in the microscale properties of the cartilage, what we are looking in a degraded region of the osteoarthritic condition. So when we characterize this, we want to see how does it look like in the histology. So the group 0 looks intact with all the layers, that is superficial, middle and deep layers intact, and that corresponds to the ORC grade 0. Group 1, the same thing as I told, that there is a damage in the superficial layer. Then in the group 2, there is increased proteoglycan damage. Group 3, erosion and the superficial and the middle layer. Group 4, there is a lot of debris and bone damage, and there is complete exposure to the bone. So when we look the same thing, characterize same thing in SEM, how does it look? In the SEM, so this is the cross section, this is the surface image. For the healthy, it looks completely fine, it's perfect, the collagens are already arranged. But when we look into the group 1, we see a lot of increased surface irregularities where there is a damage on the surface, and in group 2, we see that there is a damage in the collagen clusters, which for me as a tribologist, the surface is very important, because I want to understand how the friction is increasing or how the lubrication is taking there. So as we can see that there is a damage in formation of the clusters, there is a formation of fibrillations, and in the group 4, there is also extra attached debris of ECM matrix on the bone. And finally, the group 5, complete bone exposure, the damage of the bone. So you can see the cross section and the surface images of all the groups. Finally, when I study the mechanical properties of that, we have done the microindentation studies where we do the loading, holding and unloading regions. So in the loading and unloading region, we calculate the modulus value. So there are various theories to calculate the modulus value. Okay, when a mechanical engineer shows you a calculation of the modulus value, we need to understand the fact that there are different theories to calculate the modulus value, and which theory do we use to calculate, because is it relevant or not. In my case, I have used two theories. That's a Hertzian biphasic model, and I've used the Oliver-Fur method to calculate the modulus values. The reason why I've used that, because cartilage is a biphasic material, which is neither solid nor liquid, and it's a porous structure, and we cannot use the traditional solid mechanics models to calculate the modulus value, because it behaves both as a fluid and a solid. So we need to use multiple, we need to adjust the available theories in order to fit for the cartilage as a material. Then finally, we calculate the mechanical properties. In the mechanical properties, as we can clearly see that, if a material is strong, which means the modulus values are high. So in the group 0, which is a healthy thing, we have the high modulus value. But when we look into the 1, 2, 3, the modulus value decreases because the cartilage is failed and the mechanical properties decreases. But in the 4 and 5, the modulus values are very high compared to the group 0, which is a healthy bit. The reason is there is an exposure to the bone, and bone is much stronger than cartilage, and hence we are seeing the modulus values which are much higher there. So that's the main reason. And then when we look at tribological properties, in tribological property, if we say that a material has a higher friction coefficient, that means the material is not good. So here we can see that cartilage is one of the best tribological material we can find, because it has 0.005 or less than that friction coefficient values, which we are seeing in the healthy bit. But when we see the 1, 2, 3 and 4, the friction is increasing. But we can see that highest friction is there on the 4th group. The reason is, as I told you earlier, that there is extracellular debris which are present in the bone as well. So these debris, when we slide it on a surface, these debris are coming into the contact and are obstructing. So that is the main reason why the friction coefficient has increased. So as an engineer, when I see this, how am I going to increase the lubrication properties of this? So that's our main conclusion in the future study, where in this we have understood how the cartilage on the overall process changed from the healthy bit to the bone, how the microhydrations and the properties change, and we are able to see the ORC grades and see the properties for that. And finally, we are seeing the decreased mechanical strength and increased coefficient of friction. And finally, we are highlighting the microscale properties of the cartilage, which is very important when we look into the different solutions, lubricant-based solutions. And the future work is to identify a better lubrication solution. So whichever is available in the market, we need to identify what is it lacking so that we can enhance the micronutrients in those lubricant-based solutions, which can provide better lubrication on the surface and can withstand and provide better mechanical properties and tribological properties. So these are my supervisors, and thank you. Any questions?
Thank you very much for this very interesting talk. Are there any questions from the audience? Now then we'll start with one. You have now separated in different groups, right? And could you say how many patients you have in each group, and are they in the same age, or are there differences? Have you looked at this? Also, with the probably we know that female have more often osteoarthritis. Could you say something to this? Is the matrix stiffness there different?
So thank you for the question. So one of the main thing what we are looking here is the patients who are in the age of 60 and above, and we are also looking into the lots of difference between the genders here. And the only thing is the most of the patients and we have identified like 10 patient samples till now, and on the 10 patient samples we are taking from 2 different regions. So the main problem with respect to friction coefficient is we need to have a flat surface, because cartilage we don't get the flat surface often, so we can't measure the friction value so easily. So we have to identify which is a flat surface in the degraded region, and then we have to calculate the friction value. That's one of the main things. So in every sample, we look into the 4 different regions, and we look both on the tibia and the femur. So we look into the 8 different regions on a single sample, that into 12. So and then and with respect to the gender, that is most of the samples are female, and there is only like 3 male samples. So I have not identified the main difference yet. So that's I'm still in the process.
Yeah. Great, thank you very much. Now if I have questions.
Reed Gershik, Clemson University. There's Omer Einen out of Georgia Tech is building a sensor to detect noises in the knee. I'm curious if you think these different groups of cartilage problems would have distinct acoustic properties whenever they're subject to motion in the joint.
Yeah, thank you for your question. I do not know how the acoustics works with respect to this. However, what I would say is with respect to spectral analysis, I would say definitely there is different spectral variation in different regions of the cartilage, and Raman as a whole can be a better tool in order to identify this based on the spectral analysis, and maybe there might be a relation with the acoustic with that. I do not know that. Yeah.
Thanks.
I was just wondering, is there any clinical evidence that changing the lubrication within the joint actually has a clinical effect? So if you could actually lubricate the joint more, is there anything that indicates that has a clinical effect?
So till now we have lots of intra-articular injections, which are other than cortisol, the intra-articular injection, which are lubrication-based injections. So the main aim or the main goal of those injections are to provide the lubrication of the surface of the cartilage. So when we say for example in automobile, when we say a lubrication is failed in an engine, that's when we get a lot of problems. So as an engineering perspective, we also look at cartilage as a system where the lubrication has failed, and then the increase in friction is causing the pain. So when we say that is osteoarthritis a problem of a tribology, or like is this correlated, we would say yes, because based on all this thing we are able to identify that. So there are lubrication-based injections, but the effectiveness of that is very low, which means every 6 months you need to take another injection. But the main goal of this project is to identify what is those micronutrients that is lacking in those injections, which can stick on the surface and provide better lubrication and increase the time of the surgery. Because as a patient, so this is basically for the patients who are old or aged. So if we increase the time, so that would help them in delaying the surgeries.
So thank you very much again.
Thank you.
So we move to the last